definitely think that I'm messing it up.
I got this. For this one. That's what I got after this, but you have to divide them by the smallest number. Yeah. Oh yeah, you're right. This one, you divided it by that. Okay, I'll just put it No, I didn't. Oh, God.
Oh, okay.
And then the one between
Okay, so
Wait.
okay, so then the second time that I did it, I got 2.16.
Mine was smaller.
Okay, so just review. You guys, if you have your phone, it should be for calculating, not checking things out on media. Okay? So, we do the first one. All we're doing is we're just trying to find a mole relationship. Okay? So, some of you guys get caught up in the steps, and you don't see the big picture. Okay? All we're doing is we're trying to find the subscripts for nitrogen and oxygen and how they go together. That's all we're doing on this example. So if you get lost in the process, look at the big picture. We want to find mole ratio between the atoms. We know they need to be whole numbers. Okay? So if you look at all these examples up here, don't write them down. We're going to look at this here in a second. But if you look at all those examples, those are all whole number ratios. We want to get to where we can find subscripts, if there are subscripts, to be able to find that ratio. Because we know atoms go together in set ratios. Dalton's atomic theory says these ratios, by weight or by number of atoms, go together. We never have, in chemistry, something that's 2.5 atoms. Okay? Or 2.5 molecules. Now, we do have 2.5 moles of molecules. But that is a bigger number where you can make that justification. So, again, the more you can look at chemistry and look at the big picture and not get caught up in all the steps and what you need to do, the idea is we want to get this to a simple ratio. And to do that, that's why you divide by the smallest number of moles. So that you can make that determination a little bit easier. Some students will forget this step and then they'll get it wrong because they're rounding too soon. So this would get you 1 mole of nitrogen, and then this would give you 2 moles of oxygen. So what's the empirical formula? NO2, right?
NO2.
All right? So that doesn't necessarily mean that is the molecule. Okay? I'm going to explain what I mean by, just because we find the empirical formula, that doesn't mean that's the actual formula. It's probably a pretty good indication it is, but it doesn't. We have to get more. We have to be given more information to determine that. So, to help you out, I'm hoping, and I think this helped out last period, that when we look at these, we have 2 types of formulas we can look at. Okay? We can look at what's called the empirical formula, and we can look at this thing called the molecular formula. Now, the empirical formula is the simplest ratio that the compound will have. So H2O2, is that the simplest ratio for that compound? Can you simplify it? What would it be simplified? HO. So we see that HO is a simpler ratio than a 2 to 2.
Yeah.
Okay, so this is the empirical formula for hydrogen peroxide. Okay, this is the molecular formula for hydrogen peroxide. Does that make sense? This is the actual, when you go to the store, you get hydrogen peroxide to put on your cut to disinfect it, and it stings and it ouches when you do that, and it bubbles, okay, and fizzes. You're actually putting H2O2 on there, but the empirical, the simplest ratio for that would be HO. How about NH3? Is there a simpler way to express that? No. So guess what this? This would be both, this is both a molecular, I'm going to put M for molecular, and its empirical formula. So they can be the same. Okay? So NH3 is both considered the molecular and empirical, because it's the simplest and it's the actual formula for ammonia. This is ammonia. Right? This is ethanol. This is drinking alcohol. Okay? This is the stuff that's 10%. You go to the gas pump, get cheap gas. They have 10% ethanol. Okay? So, is this the simplest form?
No.
No. Can we break it down into a simpler form?
Or C.
No.
No, you can't because there's a problem.
Well, because this O,
Oh.
we can't divide O down. So if you have one that's a one subscript, or don't even have a subscript for one of them, it is the empirical formula always.
Why is there an H after the O?
Okay, it's how it's put together. Okay, I'm going to answer this question, but you don't have to know this. But it's how it goes together in a chemical formula. So the actual formula for this would be based upon carbons put together with some hydrogens around them. And that's the actual way in which you just show the molecule of it. These are called covalent bonds. We get to those later this year. But they've had the OH separated because they want to let you know that it's an alcohol. All alcohols have OHs shown at the end. So like rubbing alcohol would have an OH at the end. Okay? So that's just a part of organic chemistry, and alcohols is a part of that.
How does hydrogen peroxide even help with?
I don't know. It is a disinfectant. Kind of like iodine would be a disinfectant. It just kills any of those germs that could get in there.
I think it's that it just kills stuff, not just that it selectively kills germs, but like it just kills everything. And so it also kills the germs.
Yeah, and it's really weak. The stuff you get at the store is like 3%. I've got stuff that's 30%. What it will do, it acts like bleach. It actually, what it'll do, it will cause your skin to go white and actually burn your skin if you get it on you.
Why do you
Okay.
have that?
Just to show you an experiment with something that has a high percentage
Put it
of
at your
it.
house.
No, I have it here. I don't have it
I
at
thought
home.
you said I have it at my house.
No, I have that here. I don't take it home.
She's a straight kid.
Okay? All right. So, P4010, this bottom one, is that the simplest ratio? I'm about ready to be done with my reasoning here, but is that the, I was going to go ahead and write down some numbers associated with these other compounds. Oh my goodness.
So are we going to have to change from molecular to empirical?
Yes.
Test?
From empirical to molecular. So,
Oh,
what I'm going to do is I'm going to write this, to the side of this the new molecular weight of the molecular formula. Okay. So these two are both molecular and empirical, so they're the same. Can I simplify this?
yeah.
Okay. So this would be
P205.
P2O5. Okay. And so its molecular weight is 142 grams per mole. How about methane? Is that the simplest weight?
Yeah.
Okay. How about glucose?
C1H2O1.
So CH2O. And so that's going to be 30.03 grams per mole. If I add one carbon, two hydrogens, and one oxygen, add them all up, that's what I get. Is there a simpler way to do this one?
No.
No. Okay. So let's look at the ones that have empirical and molecular formulas, just to focus on those. And see if there's something in common that we can get out of looking at those for example. What do you notice that's common in those three where we're given both a molecular formula and its mass and empirical formula and its mass? All right. So this 17 is half as much as the 34. Or you could say 17 goes into 34 twice. So it's twice as the mass. So we double both hydrogen and oxygen, right? So if we double both of them, that just makes sense that we double the weight of it, right? So on this one, is that the case here? On the P4O10. Okay, so we double the number of phosphorus, double the number of oxygens, we double the weight. How about this one?
No, you have to.
What's the difference between those two?
You can multiply 6.
6. So, we divided each one of these by 6, and we got CH2O. So that means that when we would multiply each of these by 6, then we get 6 times the weight. Okay? Now, I haven't shown you any reasoning behind this, and so I'm going to have you give an educated guess and tell me what the molecular formula would be of a compound that has an empirical formula of NO2, and this is its molecular weight. Okay, I'll give you a minute. I want you to get an educated guess. I haven't shown you any steps, anything other than those examples of those three. Don't tell anybody. Write your own down. Don't discuss it with anybody. Write it down and tell me what you think the formula is. If you guys can make connections in chemistry without having to know things step by step by step, you're going to be better problem solvers, better thinkers when it comes to solving problems. Okay? If you can make that connection and not have to rely on step 1, I have to do this. Oh, I forgot step 2. What do I do in step 2? You can actually look and go, okay, what do I need to do next to get that mole ratio or get that formula? Okay. All right. I'm going to give the answer here. I'm going to give you another 20 seconds.
I don't even know how we're supposed to figure out how to connect that. I have no idea.
That's fine. I'm giving those an opportunity to see if they can do it without me telling them how to do it. Okay. So the answer is the actual formula is N2O4.
You're mad.
I have no idea how you even know
Okay, did anybody get that? 1, 2, 3, 4. Okay, 4 got it. Now, let's look back at these examples here. Okay, and I will tell you the step. All right? So I'll tell you the step, but look at these examples here. Okay? This is 30. This is 180. So 30 goes into 180 how many times? 6. So, if I want to write the actual formula out, and I'm comparing the empirical mass to the molecular mass, I know I have to increase the mass 6 times. So, every subscript increases 6 times. C6, H12O6. Real simple example, this one. I know that 17 and 34 is my molecular mass. So it's like I don't know that. And here's the empirical formula. And the molecular formula is 34. So what do you have to do to each one? You double it. Okay? Here's the next one. All right? So we know the empirical formula is P2O5. It's 142. We know the molecular mass is 284. So what do we have to do to get 284? Double it. Okay? This one. Now, what do you have to do to see how these compare? You would have to find what of this? The molecular mass of NO2, right? So nitrogen's 14.01, and oxygen, 2 of them, adds up to be 32. So that's 46.01. Now, do you guys see it?
Yeah.
Okay. So I made it tough on you because if you did it and figured it out, you probably figured out I need to find the weight of this. And once I find the weight of the empirical formula, I can figure out how many times it goes into the molecular formula to decide how much I need to multiply those by. So here's a step. So if you want to do the step, you have to have a step to do it. Then what you do is you take the molecular mass divided by the empirical mass. So you take the molecular mass and you divide by the empirical mass. And when we do that, we take 92, which is molecular mass. I'm giving you that what that is, and I divide by the empirical mass, which is 46. It goes into it twice.
And it'll always give you the molecular mass?
It'll always give you a whole number. Say, when you do that step, you'll always get a whole number that will tell you how many times bigger your formula has to be. So if it's a 2, then you multiply your subscripts by 2.
But like, will the problem give you the original?
You have to have the molecular mass. So if you get a problem and it says, determine the molecular formula, first thing you do is you find the empirical formula, find its weight, and then compare it to a given molecular mass. If it's the same, well, they're the same, right?
Yeah.
If this is 46, and I gave you, well, the molecular mass is 46, then you don't do anything to it because it's NO2. All right. Last thing I'm going to talk to you about. This is the formula for N2. Or this is the structure for N2O4. Okay? Don't write this down. This is the formula, or the structure. Okay, you'll be drawing these in the future. Okay? This is NO2. Its structure, what we think it looks like. Guess what the percentages of nitrogen are on both of these? Are they going to be the same, or are they going to be different percentages?
Same.
Exactly the same. Okay? Oxygen, are they going to be?
Yeah.
Yes. That's why you can't differentiate between these two, because guess what? Both of them give you the same percentages. They have the same ratios that are a little bit bigger. You get the same percentages, and that's why you'll find the empirical formula only when you do what we've been doing. You just have to be given more information, like the molar mass. So I would like you to attempt to practice a couple of these. All you need to really do is one, but I'm going to give you two. Page 215. Go ahead and turn to page 215.
You want us to add that on your homework?
No. You can just put this in your notes so you have another example or two in your notes.
Okay, do you want our homework? Yeah, you want us to
Your homework you can turn in any time.
Is
Okay?
it due on Monday?
Wait till I'm done and then you can turn it in. Or you can work on it. You guys probably have a good 15 minutes time I give you this. You'll do 53 and 57 if you want to practice this concept about molecular. This is the problem that most students miss. So an A student will get this problem right. A B, C, or lower will not get this problem.
Looks like I'm screwed.
Okay? So you can go ahead and practice some of these, okay? And then kind of see how they work out for you.
Okay, Merlin. So the homework, if we did complete trash on it, like, is that going to really hurt us at all? 'Cause I
It just
definitely-
goes into a formative.
Okay, because I definitely